Hey guys, we are back and today we're covering section 7.4 from our textbook, which is titled nth roots. And what that refers to is we've worked a lot with square roots in the past, but not third roots or cube roots, or fourth roots or fifth roots or sixth roots. And so nth roots refers to any kind of roots and how we can simplify any indexed root is what it's called. So on the screen in front of you, to start us off, is just a quick few examples about converting between these two forms, radical form and rational exponent form. Exponential form is often what it's called. So radical form, what that word refers to, if you've forgotten, the radical is the official name for this little symbol right here. Oftentimes we've called it the square root symbol because that's mainly what we've seen it used for in the past. But its official name is the radical. So radical form is anything that has that symbol in it versus rational exponents. Rational, if you remember, means it can be expressed as a fraction. And exponents, we know what exponents are, powers, for an expression. So fractional exponents, basically, rational exponents. So I want to look at these three examples, and I think you'll pick up the pattern pretty quickly. The first one says that these two expressions are completely equivalent mathematically. And so you look there on the left, and you have the fourth root of x cubed. That's what that little 4 right above the radical means, the fourth root of x cubed. That could be rewritten as x to the 3/4 power. And so just taking a look at this, notice that whatever power is inside the radical is our numerator in the rational exponential form. X cubed on the inside on the left, the 3 went in the numerator, the fourth root means we have a 4 in the denominator, we get x to the 3/4 power. All right, how about the second one? Second one, and I will grab my yellow highlighter. It looks like the 8th root of 2 to the 5th power could be written as 2 to the 5/8 power. And if you're looking at that, again, I'm hoping that you're seeing that pattern, 2 to the 5th inside the radical, and then the 8th root of that, we're going to put the inside power in the numerator, the radical, the nth root, in the denominator, 2 to the 5/8. So in general, just expressed generally as we often do in mathematics, x to the bth root of x to the 8th power could be written as x to the a over bth. So let's just try two more to make sure we feel good about this. And I'm going to make them a little bit harder and throw in just one other consideration. So first, what if I gave you, let's try converting both ways. What if I gave you the 6th root of 3x, that's an x, y to the 8th? So take a second and think about that one. The 6th root of 3xy to the 8th power, well, I could write that then as 3xy to the 8 over 6th, right? And we can, yes, some of you were thinking this, can we simplify that fraction 8 over 6 if it appears in a power? Why not? Yeah, absolutely we can. So I would rewrite this as quantity 3xy to the 4/3 power. And that's how I would convert it into rational exponent form. Notice I did include those parentheses. That's another thing I wanted to mention. We are raising that entire expression 3xy to the 8th power originally, and then taking the 6th root of it. So we do need those parentheses in there. One more example. Let's go the other way. If I asked you what, let's go with 14x all to the 1/2 power. And this is maybe the biggest one that I want you to know and just memorize. What is the 1/2 power? So if we're going from rational exponents to radical form, the 1/2 power, the numerator is the power inside, so 14x to the 1th. And then we're taking the second root of that. The denominator is what root we're taking. So if we stop writing some of the kind of extra bits, this is just the square root of 14x. 14x to the first is just 14x. And oftentimes we will just leave off that 2 if it's a square root, because if there is no index written here, then it is assumed to be a square root. So we could just write it as the square root of 14x. So hopefully these examples made a lot of sense to you. And one big takeaway, I said there was one I want you to just have memorized and never have to think about again. If something is to the 1/2 power, it is a square root. Okay, 1/2 power is equivalent to square root. So that's kind of a little bit of pre-lesson just to start thinking about how we can write things in different ways. But let's go ahead and move on to our main subject, which is nth roots. Now, if you're looking at the screen right now, you don't necessarily have to write all of this down. I just want you to look at it and process it and hopefully make sure that it's making a lot of sense in your mind. It says, okay, nth roots. 2 is the square root of 4, and we know that. That means that 2 times 2 is 4, or we could write that as 2 squared equals 4. So these are somewhat inverse ways of writing it. 2 squared equals 4. Well, then the square root of 4 equals 2. Let's do another one. 2 is the cube root of 8 because 2 times 2 times 2 equals 8. Yeah, we know that. So that means that 2 cubed equals 8. That also means that the cube root of 8 equals 2. And that one on the right that I just wrote, what is that saying? That's asking us what times itself 3 times would equal 8. That's what the cube root means. What times itself 3 times would give us 8? And the answer is 2. Moving right along, 2 is the 4th root of 16. That's because 2 to the 4th power is 16. 2 times 2 times 2 times 2. We could also equivalently say that the 4th root of 16 is 2. What times itself 4 times equals 16? 2. And then last one here, 2 is the 5th root of 32 because 2 times 2 times 2 times 2 times 2, or 2 to the 5th equals 32. And what is the equivalent fact we could write from that? The 5th root of 32 equals 2. So just reminding ourselves, what do these words, the roots, the squares, and things like that mean? If we are looking at an nth root, whatever number n is, if we are looking at an nth root, we are asking ourselves, what times itself n times equals this number? So the 4th root, what times itself 4 times equals 16? And so that's what we're going to be working with, except we're not just going to be working with numbers, we're also going to throw variables in there and such, as we have all year. So here's kind of, again, some of those official terms and a nice diagram for you visual people out there. The index, I mentioned that word earlier, is what root we are taking. It's that little n above the radical. So the nth root of 50, you see the radical sign, and then what is underneath? It's called the radicand. So let's work through a couple examples. I'm going to start with one we kind of know. How do we simplify a square root? That 2 up there is not strictly necessary. Remember, if it's not written there, it's assumed to just be a square root, but it doesn't hurt to have it up there. So what do we do to simplify a square root? Well, we start breaking things down. 50 is 25 times 2. We're going to find those prime factors. 25 is 5 times 5. And then, if you've been thinking about it, we've always said, okay, well, I mean, we have a pair of 5, so we can pull them out. That's the rule we learned. 5 with the 2 on the inside because it didn't have a pair. And I know we've talked about pluses or minuses in this chapter. We've started saying when we're talking about functions, we're only going to take that principal root. So for now, just to keep things consistent with this chapter, I will leave the plus minus off because we are talking in the context of square root functions a lot. But if you've ever asked yourself, okay, wait, hold up. Why are we taking a pair out? Why are we taking a pair out? Here's the reason. That right there, if it's a square root, if it's the second root, we need to find a group of 2 in order to pull something out. And so that's why when we found a pair of 5s, we could pull them outside the radical and we're left with just 5 root 2. Now, based on some of those words I emphasized, you might have an inkling of what's coming next. How do I simplify a cube root of 40? Well, we're gonna do the exact same starting point. 40 is 4 times 10. 4 is 2 times 2. Those are both prime. 10 is 2 times 5. Those are both prime. So we found those prime factors. Here's the question now. What are we looking for in order to pull them outside of the root? It's not a pair. It's not a group of 2 anymore. We are looking for groups of 3 because it is a cube root. We look here, we say, okay, well, there is a group of 3. We have 3 2s. Well, this equals 2 times the cube root of the 5 that was left inside there. 2 times the cube root of 5, because 5 was left inside and we had a group of 3 2s. So this is the number one thing you need to know about nth roots, is when we're simplifying them, what are we really looking for? We are looking for groups of n. Cube root, we're looking for groups of 3. Square root, we're looking for groups of 2, our usual. 7th root, we're looking for groups of 7. And that's how this is going to work. Try this problem real quick. Pause the video, try this problem, break down 64, and look for groups of 4. All right? Once you are done, go ahead and unpause the video and see if your result matches mine. All right, there's my work on the screen. 4th root of 64, I was looking for groups of 4, broke it all down. Turned out 64 is just 2 times 2 times 2 times 2 times 2 times 2. So we have one group of 4, we can pull 1 2 outside, and we have 2 2s left inside that radical. So you can see my top line there, 2 times the 4th root of, there are my 2 2s left inside, and I just simplified 2 times the 4th root of 4. So hopefully that one went well, and these 3 examples kind of make sense as we're doing just numbers, taking the nth root and always looking for groups of whatever n is. The 2nd root, 3rd root, 4th root. All right, so let's simplify a couple of these. Notice that this first one very clearly asks us for both answers, the plus or the minus. So our final answer should include both of those roots. It looks like a square root. No index is written there, so we can assume we're looking at a square root. 25 is 5 times 5. Square root, we're looking for groups of 2. So it looks like we can pull a 5 out and have no numbers left inside. That's nice. What about that x to the 4th? X to the 4th, if you remember our prime factorization, what it looks like, x times x times x times x, right? There are 4 of them, x to the 4th, all multiplied together. How many groups of 2 do we have? There's a group of 2. There's a group of 2. So we can pull out 2 x's and have nothing left over inside. So our final answer on this one is plus or minus 5x squared. Looking for those groups of 2. 25, we had a group of 2 5s. And then 4 x's, we're looking for groups of 2. So we can kind of look at it like this. We have 2 of them, pull them both out, nothing left over. Plus or minus 5x squared. How about the next one? The next one is asking not for the principal root, but for the negative root, the negative cube root of 16x to the third y to the fifth. Let's start. 16, I'm going to say is 4 times 4. 2 times 2, 2 times 2. Broken it down as far as I could go. I am looking for groups of 3. It looks like we have one group of 3 there of those 2's. So when I'm writing my answer, I'm looking for that negative root we said, because there's a negative out front. We can pull 1, 2 out, and it looks like we will have 1, 2 left inside because of this guy right here that didn't get used. It didn't have a group of 3. So that deals with the numerical part, 16. X cubed, picture them. I'm not going to write them out this time because I want you to start picturing them in your head a little bit. We have 3 x's. We're looking for groups of 3. There's our group of 3 and nothing left over. So the cube root of x cubed, we can pull an x out, nothing left inside. What about y's? We had 5 y's, so we can group 3 of them together. And it looks like we'll have 2 that are left on the inside because they couldn't form a group of 3. So we had one group of 3, we can pull a y out. And then we have y squared left inside there. So again, with those y's, there were 5 originally. We could pull one group of 3 out, and then there are 2 left inside that radical. So negative the cube root of 16x cubed y to the fifth came out to be negative 2xy times the cube root of our leftovers, 2y squared. All right. What if we start seeing powers inside of powers? Negative the square root of y squared plus 2 to the 8th. Well, there are a couple ways to go about this one, but first, the first thing I want you to do is just think about, what is this inside actually saying? This inside is saying negative the square root of y squared plus 2 times y squared plus 2 dot 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 times y squared plus 2, and that's happening, I can't draw symbols to save my life. There we go. That's happening 8 times. It's a little bit better. I just didn't want to write them all out is all. So if it's happening 8 times, that essentially means we have 8 of these things multiplied by each other. How many groups of 2, because it's a square root, make sure that's visible, how many groups of 2 can we see? Well, there are 8. So 1, 2, 3, 4. My fingers are not nimble, but if I did it like this, it'd be a little bit easier. We have 4 groups of 2 out of those 8 expressions, factors that are being multiplied. So we could say then, look, we have 8 of them, negative y squared plus 2 to the 4th power, because we had 4 groups of 2 with nothing left over. All right, no need to multiply out those insides all the way. That would take forever, and none of us really wants to do that. That negative came from that starting question. Negative the square root of y squared plus 2 to the 8th power equals negative y squared plus 2 to the 4th power. Now, I do want you to think about this one other way, because I mentioned there were a couple different ways to approach this problem. I'm going to draw it in blue down here to the left and see if you are good with what I drew. Sorry, got ahead of myself a little bit there. Sometimes, and some people prefer to think of this in rational exponents. What we started this video with, y squared plus 2 to the 8th over 2th power, because it's a square root here, we could convert it to that. And then, I mean, well, then what is it? Then it's just negative, and simplify that fraction, y squared plus 2 to the 4th power. There might be times when this is a more straightforward way of looking at it, thinking about it, converting it to rational exponent form. And some of you might want to do that like all the time because you really like doing that. But these are just 2 ways you can think about this problem as you're going through. All right, kind of a challenge problem to end this part of the video. I would love for you to pause the video and challenge yourself with this one right now. The 5th root of 128, x to the 15th, y to the 9th, z to the 22nd. Not a harder problem conceptually, just higher numbers, right? So try pausing the video, work this out, and then I'm not gonna work it out right now. When you unpause it, I will work it out fully. So I won't do it when it's paused. I'll talk my way through it and work it out fully once you unpause. But try this one on your own right now. And then after you've done that, go ahead, hit play again. All right, so by now I'm hoping you've had the chance to try this out. 5th root, I'm looking for groups of 5. 128, I don't know too much about. I'm gonna keep this red just to stay consistent. But I know it's 2 times 64. 64 is 8 times 8. 2 times 4, 2 times 4, 2 times 2, 2 times 2. 128 is just a bunch of 2s. So if I'm looking for groups of 5, let's see how many groups of 5 we can find. There's one group of 5, and it looks like I have this 2 and this 2 that were left over that don't form a group of 5. So I'm gonna come over here and say, okay, numerically, I can pull a 2 out. I'll leave lots of room for my variables. And then I had 2 2s left over. Put them back in there, it's 4. 2 times 2, multiply them together is 4. Now let's talk about those x's. I have 15 x's. I don't have enough fingers to represent that. 1, 2, 3, 15 x's. How many groups of 5? Well, in 15, there are 3 groups of 5 and nothing left over, right? What about y's? I have 9 y's. I need a group of 5. Here's my group of 5, and there are 4 left over. I can pull out 1 y and have 4 left over. Not quite enough to form a group of 5. And then how about z's? There are 22 z's total. So I can make 5, 10, 15, 20. I can make 4 groups of 5 for the z's, z to the 4th, and have 2 left over here. 2 left over there. So 2x cubed y z to the 4th times the 5th root of 4y to the 4th z squared. And there we are. Okay, so that's our 5th root, kind of a tougher, higher numbers, problem. But again, conceptually, I would argue it's not any harder than what we did before. Same idea. All right, now, couple other things to be aware of. And the first one is this kind of, it's sort of an edge case. It's a case that isn't immediately intuitive why we might need to use absolute value when simplifying these radicals. But I'm going to try to demonstrate that for you right now. So if you're looking at this, it says when you find the nth root of an even power and the result is an odd power, you must take the absolute value of the result to ensure that the answer is non-negative. And you might read that and say, wait, what? Why do I need to make sure it's not negative? Like, I mean, it could be negative, right? Maybe, could be. Well, let's take a look. And I'm going to try to demonstrate this with those 2 arrows by solving this first problem, this first example, 2 different ways. So square root of -5 squared. Now, there are some of you out there that might say, oh, well, this doesn't look that hard. -5 squared, I should probably do that exponent first. So -5 squared is positive 25. And I know that the square root of 25 is 5. Done and dusted. That's my red crew. My blue crew says, well, hold on just a second. We've got the square root of -5 squared, And I don't know everything, but I do know that a square root and a squared kind of cancel each other out, giving me -5. So who's correct? Red or blue? They both have compelling arguments. Red team is kind of correct here. And here's why. Here's the reason. It has to do with, if you remember that graphic that we showed when we were first getting into square root functions, where we have like a sideways parabola, and then we said, well, to make it a function, we're only going to take the positive result as the principal root. If it's kind of ambiguous, we want to make sure we're taking that principal root. And so mathematicians developed this rule to make it a function, to make sure we always get the same answer when working the same problem. And they said, if you start off with, changing color of my highlighter, an even power, we had -5 to the second power, it was an even power, and then it turns odd when we simplify. There's that invisible one, right? -5 to the first power. If you go even and turn odd, then we want to make sure, and we could draw it either of two places, we want to make sure that we are taking the absolute value to get the exact same solution as, no matter how we work this problem. Now, if that explanation kind of went over your head a little bit, if it didn't make tons of sense, I'm never going to ask you to explain this rule, but you do need to be aware of it. And so here's what, if you're wanting to just say, okay, I know there's a rule and I'm going to learn when to apply it and leave it at that. Starting with even, ending with odd. You got to take the absolute value. So similar problem over here to the right, we've got the 4th root of b to the 20th. Well, we have 20 b's, and so groups of 4, we can make 5 groups of 4. It would be b to the 5th, except we notice, okay, hold on. We went from an even power to an odd power. I'm just going to surround that whole thing in absolute value to make sure it's the positive principal root. Even power to an odd power. That's the only time we need to worry about this. Okay? So again, a couple more from the book, just demonstrating this. A, I left in there. The 8th root of x to the 8th, we want to say is just x, you know, and there's a group of 8 right there, and we pull it out. But we want to make sure that the 8th root of x to the 8th, we went from an even power to an odd power, that x to the 1th. So we have to take the absolute value. Similarly, right here, if you look at it, we've got the 4th root of 81 times quantity a plus 1 to the 12th. 81 is 9 times 9. 9 is 3 and 3. This 9 is 3 and 3. We're looking for groups of 4, and I dare say we found a group of 4. 3. A plus 1 to the 12th power. And we're looking for groups of 4. So we have 12 of them, looking for groups of 4. 4, 8, 12. We can find 3 groups of 4. A plus 1 to the 3rd power. But did we go from even to odd anywhere? Here we go. 12 to 3, even to odd. I'm going to surround that in absolute value. If you're wondering why the 3 doesn't get surrounded in absolute value, well, I mean, it wouldn't make a difference on this problem, but essentially it's because it's a number. We can see that it's the positive principal root of 81. And so we don't have to put absolute value around it to ensure that it is, because it already is the positive principal root there. So even to odd, make sure you are putting some absolute value around it. I'd like you to take a look at these 2 problems, check them out and try them, and then unpause the video and see if you got what I am getting. All right, and hopefully you have worked those out. On the first one, I got that the square root of 100x to the 10th came out to be 10 times the absolute value of x to the 5th. Again, even to odd, so we made it absolute value of x to the 5th. And then on the second one, square root of 64, y plus 1 to the 14th. Square root of 64 is 8, and then y plus 1 to the 14th 14, we're looking for groups of 2. So it's kind of like 14 divided by 2. We have 7 groups. And we went even to odd, forgot to highlight those. So we get 8 times the absolute value of y plus 1 to the 7th. All right, so 2 more as we're simplifying all these nth roots. I know we're doing lots of practice today. I want to talk about one with a negative. The cube root of negative 27, x cubed y to the 20th. I'm not worried about the x cubed y to the 20th. If you've made it this far, hopefully you're feeling pretty good about simplifying those variables. But what about the cube root of negative 27? What times itself 3 times equals negative 27? Well, this is where we got to think a little bit more, because I recognize 27. 27 is 3 times 3 times 3, right? 3 times 3 is 9, times 3 is 27. So the cube root of positive 27 would just be 3. What would the cube root of negative 27 be? Well, I want to show you, what is negative 3 times negative 3, positive 9, times negative 3 would be negative 27, just what we wanted. The cube root of negative 27 is negative 3. And you'll start seeing these patterns with these odd roots. We can find a real, not imaginary, a real root for an odd numbered root of a negative number. So the cube root of negative 27, again, we could say that's negative 3 times positive 9. That's negative 3 times negative 3. And here's our group of 3. So negative 3 x cubed, and then the third root of that, so we can make one group of 3 to pull out, nothing left over. Y to the 20th. How many groups of 3 are there in 20 of them? 3, 6, 9, 12, 15, 18. So I have 6 of them I can pull out and still have 2 left over inside for those y's. Negative 3x y to the 6th times the cube root of those 2 y's we had left over, y squared. Did anything go even to odd? X's went 3 to 1, that's odd to odd. Y's went even to even, so no absolute value needed. All right, last problem of the video. Try it, and then I'll work it through kind of all together, make sure we end on the same page. So go ahead, pause it, try it, and then unpause it. Okay, the 4th root of 32, x to the 12th, y to the 4th, z to the 16th. 32, I'm gonna say, well, that's 4 times 8, 2 times 2, 2 times 4, 2 times 2. I'm looking for groups of 4. There's my group of 4, and it looks like I have one little guy, 1, 2 left over. So I'm gonna say this is 2, leave lots of room, and the 4th root of, I have a 2 left over. How about x's? And I should move this over a little bit, give myself a little more room. X's, I have 12 x's, groups of 4, 4, 8, 12. There are 3 of them. 3 groups of 4 and nothing left over. Y's, 4 of them, I'm looking for groups of 4. I can pull out one group of 4, nothing left over. Z's, 16 groups of 4, I can make 4 groups of 4, nothing left over. And so this is looking pretty good. Last thing to check, any absolute value needed. Did I go even to odd anywhere? It looks like I went even to odd with my x's, even to odd, invisible 1 there, with my y's, even to even with my z's. So all that needs absolute value would be the x cubed y. 2 times the absolute value of x cubed y times z to the 4th times the 4th root of 2. So nth roots, again, they're kind of like square roots, big takeaways. If you're looking for an nth root, you're looking for groups of n, not just pairs anymore, groups of n. I told you at the very beginning, one thing I wanted you to just start locking down, something to the 1/2 power is just the square root. We saw how to, if I scroll up a very long way, how to convert from that radical form to the rational exponents. And then that one thing, tricky thing we got to be on the lookout for, which was if we go from even to odd with any powers, we have to enclose it in absolute value to ensure we're getting the principal root. But guys, that is it for nth roots. 7.4. If you have questions with those practice problems, circle them, get in touch so I can help answer them. And I will see you guys next time.